Okay, so today we're doing the reactivities of metals lab. There's a lot of little experiments, and what we're trying to get at is the trend in reactivity of metals across the periodic table. So we'll be investigating metals which are in the same column of the periodic table and see how the reactivity changes as you move down a column. And then we'll be looking at metals that are in the same row of the periodic table and see how the reactivity might change across a row. And we're going to be investigating this in several different ways. So there's basically three types of reactions that we'll be doing today. The reactions of metals with water. So here we see 2 sodium plus 2 water is going to make sodium hydroxide and hydrogen gas. We'll be able to identify that these reactions occur in several ways. We'll see the metal itself disappear. We'll see the generation of hydrogen gas, which is flammable, and then the sodium hydroxide will turn the solution basic. And there are 2 different ways that we have of telling that a solution is basic. Metals will also react with acids. Now you'll see that many of these reactions are just what you might have expected based on maybe like Batman cartoons or something. The metals will react vigorously with the acid. And then some other metals actually are completely non-reactive with acid. And we'll be able to see that and be able to determine a trend in metal reactivities with acid. Now in this case you don't make a basic solution, but you do consume H+, and so the solution will be less acidic at the end. And again, it generates hydrogen gas, and the metal is turned into an ion. It's been oxidized. And then lastly, we're going to investigate reactions of elemental neutral metallic metals with metal cations of another metal type. So here we have iron sulfate. Here the iron is in the 2+ state. With copper solid, the copper is in a 0 oxidation state. And that may react to form copper sulfate. Now the copper is in the 2+ state. And iron metal, which is in the 0 state. Now you can see there's a bit of symmetry to this reaction, and so I've actually written the reverse reaction on the bottom, where iron starts in 0, iron solid, and ends in 2+ to go to iron sulfate. And the copper instead starts at 2+ and in the copper sulfate form and goes to 0 copper solid. Now, only one of these reactions is going to be spontaneous under the conditions that we run today. And so hopefully you'll be able to identify what we call an electrochemical series, which is saying which metals in their neutral metallic form are most reactive. Now, looking at this reaction, it's a bit of a tug of war between the copper metal on this side and the iron metal on that side. If copper metal is more reactive than iron metal, then the top equation will be the spontaneous one that occurs in nature. If instead iron metal is more reactive than copper, then the bottom one will be what happens in nature. And so we'll use experiments to determine which metals are most reactive and make predictions about which of these then is going to be the spontaneous direction for this reaction to flow. And so we'll tell which metals are more reactive in different methods for all of these. For the first 2, the reaction of metals with water or acidic solution, then we'll be able to just observe how vigorous the reaction is. Some of the reactions will happen almost violently with bubbles pluming out of the reaction. And some of them will happen slowly, and some may happen not at all. With the metals, we can begin to build an electrochemical series in the same way by reacting the metals with acids and seeing which ones are going to react more vigorously. That'll give us an idea of the electrochemical series, and then we'll be able to actually run these where we pit the metals against each other directly. It's like reacting them with acid is timing them in a race by themselves. And then here we're pitting them directly against each other, and so we can make that direct comparison, like seeing, instead of looking at the times, seeing who crosses the finish line first. So we'll have one way to predict our electrochemical series, and then we'll verify it through these sorts of reactions here. Ultimately, we're looking at metals that are in the same column or in the same row of the periodic table, and we're going to make a distinction between the main group metals, which are ones like in columns 1 and 2, and over on the other side of the periodic table, like aluminum in the P block of the periodic table, as compared to transition metals that are in the D block of the periodic table, and there could potentially be some complexity and some differences between those two groups. So anyway, let's get started. Okay, for these first reactions, we're going to be looking at how metals will react with water. So I'm going to, I have a beaker here that's filled with just ordinary water, and I'm going to go ahead and fill a test tube with water all the way to the top, and then invert the test tube into the beaker. And the idea here is to have as little of a bubble as possible at the top of the test tube. I'm not actually particularly good at this, so it looks like there's a fair amount of air at the top, but I think we'll be all right. Here I have sodium metal. Sodium metal is kept under mineral oil because it is so reactive that it will react with the air, and we don't want that to happen. Whoops. I guess my tongs don't fit in there, so I'll use a spatula. I'm getting out a small piece of sodium metal, and your lab manual says to wrap the sodium metal in aluminum foil. And I simply couldn't find the aluminum foil in the stockroom, so we're gonna do a modified method here, where there is no aluminum foil.
That's Dada.
Hi,
Yeah,
Tina. This is my daughter Tina. She's helping me today.
Yeah.
Without school, I just needed some help. Well, I got a rather large piece of sodium there, so I'm going to go for a smaller piece, as long as that one fell in.
And I don't know what Daddy's doing.
Okay, so we're going to put the sodium in the water and underneath the test tube. And you saw it was immediately reacting. It was forming bubbles, and now this test tube is filled with gas. And that's it, the sodium is gone. It actually escaped, and now it's bubbling on the surface. Oh, gosh, it actually kind of smells. Excuse me. I forgot my goggles, and Tina's got goggles too. Can you put your goggles on, hon? Oh, let's do real goggles first.
Okay, but my sunglasses
And
won't
then
go.
just like so. All right. So we're going to do two tests on the reaction products here. The first is to test the gas that we collected in the test tube. We want to see if it's flammable gas.
Mm-hmm.
So I'm going to light a match. I'm perhaps going to light a match.
It's a green match.
It is a green match, isn't it?
That's weird.
There we go. Okay.
Oh, it stinks in here.
Hopefully you saw that little pop. That tells me that the product of that reaction was flammable. And then we're going to take a piece of litmus paper. This is an acid-base litmus paper, and it starts...
It's paper.
Yep, it's paper. Oh, hey, you took your goggles off. It starts basically a pale pink color, but when we dip it in the solution here, hopefully you can see that now it is blue color, and that, good job, team. And that indicates that the solution is basic. It means the opposite of an acid. Now I'm going to replenish this water, and we'll do the same thing with calcium metal instead of the sodium metal.
There's the letter C on that.
On what?
That.
Oh, there is, isn't there?
C.
How about that?
Yeah.
Okay, again, we'll fill the test tube with water.
Water.
And we'll invert it into the beaker, hopefully getting as much of the air out as we possibly can. I think I did a bit better at the air bubble that time, although I made a mess on the bench while I did it. Okay, and now I'm going to use my tongs to pull out a piece of calcium metal.
Calcium. Starts with either K or C.
In this case, it starts with a C. So we'll put the calcium in the water, and it is clearly not reacting the same way that the sodium did. It is, however, generating bubbles. If you look down there, the calcium metal chip is now surrounded with bubbles, and they're slowly bubbling up. I want to make this go quickly, so I'm going to put in a few more calcium chips just to make this.
A bunch.
Yeah.
That's three.
We get to play fast and loose here.
Why do they need to be
And
there?
I'm going to try and get as many of them captured underneath this test tube as possible so that we can collect all of their bubbles. There we go.
Why do you want bubbles?
Just because the bubbles are the product of this reaction. Ah, I got them all. Okay, so we'll leave that for a minute. You know, with 4 big old calcium chips, it actually is bubbling rather vigorously. And I'm overflowing my beaker, so I'm going to go grab some paper towels.
Daddy, your test tube. Your test tube.
Honey. I guess we'll have to redo that one. Was it floating up?
Yeah, so I tried to put it down, but then it fell out.
Thank you, hon. Well, you know, we may be able to salvage this. If I just collect as many bubbles as gosh. I guess things float. Okay, let's be really reckless. And just see if we can light the gas as it's coming off. Ha. I think that achieves the same effect. We're igniting the bubbles.
Why is the fire coming out if it's been put in a beaker of water?
Because the fire is happening right above the water.
Oh.
Okay, and we'll do the same thing. Oh, by the way, this is Slothy Dothy. I'm honestly not sure how she ended up in my arm here.
Me neither. She's my stuffed animal.
I was moving her when the beaker tipped over. Okay, and again we can see that the filter paper
It's even bluer.
turns blue. So the products of this reaction are basic. Okay, I'm gonna stop this recording and clean up my terrible mess here, and we'll do the next part of the lab. Okay, so now we're going to look at the effect of metals reacting in water. And we're including metals and one non-metal. So what I have here is an array of beakers, and we'll give you a closer look at them in a moment. They're all filled with some deionized water, and I'm going to put in each of them a few drops of phenolphthalein. So phenolphthalein is a chemical substance with two wonderful properties. The first is that it manages to string together 5 consonants in its name, phenolphthalein. And then the second is that it will change color depending on the acid-base conditions of the solution that it's in. So phenolphthalein will be colorless in neutral and acidic conditions, and it will turn pink under basic conditions. So I'll put a little drop in each of these beakers. If I can get the dropper out. Okay. And now we're going to give you a closer look at what's going on here. Oops. So I did have this all set up nicely so that we can look at the different beakers. Hopefully you can see the labels there. So we have some lithium, sodium, and then potassium. And those are all in the same column of the periodic table, and they've been neatly arranged to reflect that. And let's see what happens when we add a little bit of each of these into the water. So let's start with the potassium. So we keep all 3 of these metals under mineral oil. That way, that way they are not exposed to oxygen while we store them. And they are all soft, pliable metals. Here I have my scupula, and I'm just cutting a little chunk of potassium off of the main bit. I can cut it like butter. And if I turn over to show the recently cut side, you can see that it is shiny, like any other metal. So let's put the potassium in the water and see what happens. You can see that it is...
Daddy, how's your fire in water?
So it is bubbling. It's generating some sort of a gas that is obviously flammable, generating enough heat to ignite that gas. And that's potassium. You can see actually it sputtered so much that it sprayed some pink phenolphthalein solution into the neighboring beakers. Now,
Are you putting some more different stuff in?
yep, this one now is sodium. And
What are you putting it in?
the sodium's going to go right here. And again, it is a soft metal. I can cut it like butter. We'll put it in there into the sodium.
Is everything going to turn pink?
That's making it turn pink, yeah.
Is anything going to turn in a different color?
No, all pink today. Oh, we'll have different colors later, actually. Just not for a while. So there's the sodium. And then even though it's not normally a part of this lab, I decided I'd give you guys a bonus and do some lithium.
What is lithium?
So the lithium we have in little pellets. I didn't have to cut it, but we'll put some lithium in the water up here. You'll see the lithium
The lithium, I think I should get it.
not reacting much at all. Boop, boop. I'll stir it a little bit with a matchstick I found. Okay, just for fun, let's do a little bit more potassium. I really should have presented these in the opposite order so that you could have the best for last, but we'll just go back and we'll redo the potassium. So here's a bit of potassium. Needs to get through that mineral oil first. Uh-oh. Well, that's a bust. Here, I'm determined to make this fun, so I'm going to get another piece of potassium,
Same one.
Careful, hon. Don't push my chair with my laptop on it.
Same.
Yeah, this is the same one. This is the potassium. Okay, hopefully this one will be a little more reactive for us. There we go.
It was supposed to have fire.
I know. I'm a little disappointed in all of these. Well, I think their oxide layers are just a little too thick.
Maybe you should just stick to the one you have.
There we go. Okay. So now we're going to move a little bit to the right. And here we see we have calcium and magnesium. Let's do the magnesium first. Magnesium, you've seen magnesium ribbon that we've used before. In order to make this reaction go a little more rapidly, we're going to use little magnesium flakes.
What color, Dad?
Right there. We'll put the magnesium in, and we'll leave that for a moment.
Is it going to turn a color just like the other one? The other one's a color now.
Sure will.
I wonder what color.
And then the calcium here, they look like they're covered in thin layer of moss or something. That is a calcium oxide layer on the outside. This is not as soft of a metal, and I'm going to put that in there, and we'll just let you watch that for a few minutes.
It's turning pink. That's the one. Daddy, which ones are going to be different colors? The one is either pink.
So I'm going to help you see a little bit of what's going on with the magnesium. Oop, sorry. Oh, that's lithium. You can tell I'm not a very good camera person. So there's the magnesium. You can start to see a little bit of pink forming right around the flakes. And we'll see some bubbles form. Hi there.
Not soap dispensers today.
Oh. You've got two little things. Yeah, sorry, we're filming a lab. Okay. So we can come back and revisit that magnesium in a little bit, because these next two, aluminum and sulfur, we need to leave for a long period of time. I'm going to move over here. Oops. There we are.
Hey.
So aluminum, just what you would expect, is shiny metal, but we have here aluminum that's been ground into a fine dust. And that's going to give it the best chance of reaction, giving it lots of surface area. We'll stick the aluminum in there. And sulfur as well. This is our only non-metal. Of course, sodium, magnesium, and aluminum and sulfur are all on the same row of the periodic table. And so they are going to help you to see the reactivity trend across the row. And here is the sulfur. It's a yellow, smelly solid. Okay, now I'm going to leave these for about an hour I'll use some time acceleration, so it'll be a few seconds for you. We'll come back in an hour and see how the sulfur, the aluminum, and the magnesium look after that time period. Okay, Gene, let's clean up. Okay, so it's been about an hour. We can see that the sulfur appears not to have reacted at all. The aluminum also has not reacted at all, and that's a good thing. If you've ever been in an aluminum canoe or something, then you're grateful that the aluminum does not react with water in the same way that potassium does. And then there's the magnesium. There we go. And there's the magnesium. It certainly was a lot slower than the others, but it eventually did turn the solution a little pink, and there are a little bit of bubbles forming. But it's a very slow reaction. It took a whole hour, and honestly, it wasn't very pink at the end of the hour, and so I cheated and put a little base in, just to make the demonstration a little bit more obvious to what it's supposed to be. If we had left this magnesium for several hours, then it would look like it does now on its own. The magnesium, am I still pointing at magnesium? I am. The magnesium would be and should be pink. Okay, now we're going to be reacting metals with acid. So for this first one, I've prepared here a 1 molar solution of hydrochloric acid. Now you were asked to calculate exactly how much of the 6 molar hydrochloric acid you need to use, diluting it to a total final volume of 150 milliliters to make 1 molar hydrochloric acid. And I'll leave that to you to do those calculations yourself. Sorry, there we are. So this is our 1 molar acid. And here I have a short strip of the, of the magnesium metal ribbon. And we're going to do the same thing we've done, where we fill test tube with water. Sorry, it's taking a bit.
You're filling it with water again?
Yeah.
Are you trying one that might sink?
Yeah, I'm going to hold it this time. I considered redoing that last experiment, but I thought I'd just kind of leave it. That's how science goes. You can learn from your mistakes.
Dad, you should zoom in.
Yeah, I'm sure there's a lot of ways I could do better videography than I'm doing. But we're just going to make do with my best. Okay, so I've filled this with water, but remember the beaker is full of 1 molar acid. So we'll invert it and put the magnesium metal in and underneath the beaker. Okay. And Tina, can you move your head? Actually, the students need to see. So it is bubbling vigorously. We're collecting those bubbles. Now we are collecting those bubbles. And we will soon test them to see if they are going to be flammable like the bubbles from before. Tina, can you let me do it, please? Thank you. I know. You were helping. Okay, so it's taking a bit of time, but it's certainly going much faster than the magnesium in the fume hood did when it was reacting just with water. So this magnesium is reacting with acid much more rapidly.
think. We're just about done here. So I'm going to get a match ready. And then we'll lift it up and we'll check for the pop. There we go.
Is it going to make a loud boom sound?
Just a little one. So that was indeed hydrogen gas. Now we won't check the pH of this solution because it was 1 molar hydrochloric acid. Remember, it's less acidic now than it started with, but it's still overall acidic, so it wouldn't turn the litmus paper blue at all. Now we're going to fill 3 test tubes with 3 molar hydrochloric acid, which I just have a sample of. What's that, team? No, why don't you let me do this?
Okay. But I don't know how to pour a milk gallon.
You can pour a glass of milk like a pro, but hydrochloric acid maybe will let me handle that.
Yeah, I think it's also because you need a certain amount.
Okay, now we're going to compare magnesium, aluminum, and sulfur that lie all in the same row of the periodic table. So I'm going to cut another strip of magnesium here.
Daddy, they don't see you that much.
Oops.
No, they do.
Well, I lost that piece. I'll cut another one. Okay, and these I'll do a little bit closer to the camera for you to see. So here is the magnesium in 3 molar hydrochloric acid.
I can't see.
Sorry, hon. You can see the video after when we edit it.
Ah, now I can see.
Okay, so it's bubbling and fuming. Now, we'll do aluminum. So again, we have this fine aluminum powder, and making it in a powder form increases the reaction rate, such as it may be. So there's the aluminum. And while the aluminum did not react at all in the water, you can see the slow, gentle formation of bubbles here in the acid. So aluminum will dissolve in acid, albeit slowly. Agitate it a little bit, and you can see that although the aluminum powder is settling down, there are still teeny tiny bubbles that are up in the solution. And if you left that long enough, then the aluminum would dissolve. Oh my goodness. I don't need that, thank you. Okay, and then lastly, we're going to do sulfur. Sorry, I thought I had it already, but I don't. Here it is.
So much sulfur. Do we need the whole
And
jar?
here's the sulfur. No, we only need a tiny, tiny bit. And just like in the water, the sulfur is just going to sit on the surface there. Oops, it's not focusing too well, sorry. In fact, it's not even sinking to the bottom, it's kind of floating up there at the top. I can try to agitate it, and you see nothing is going to happen here with the sulfur. Okay. Okay, so now we're doing the reactions of transition metals with acid. We have 4 test tubes here filled with 6 molar hydrochloric acid. And I know that the resolution of my camera may not be great, my videography is not very good, and you may be watching this on a cell phone, which would make it maybe hard for you to make fine comparisons. So I'm just going to say that I am doing these metals in a certain order for a certain reason, to help you with your interpretation of what you observe. So we're going to start with copper. This is just some copper wire, and we're going to put the copper into the hydrochloric acid solution. And let's see what it does. And what I see is that the copper maybe is becoming cleaner as crud and corrosion on the outside gets cleaned away by the acid, but the copper wire itself isn't being dissolved at all. So that is copper. Next we're going to do iron. Where's my iron? Here we have a fine powder of iron. Tilt that a little bit. Okay. So here is iron in acid. And you can see it is bubbling. Hopefully that helps a bit. The bubbles are causing the iron to tumble around and mix up a little bit. And we're generating, again, hydrogen gas. We won't test that here with a match, but we could. So that is the iron reaction. Next, we're going to do chromium. Again, we have a fine powder of chromium metal, and we'll put that in to the hydrochloric acid. Actually, I'm surprised at this result. Oh, shoot. Chromium coarse particles. Okay, well, it could be that this chromium metal, although it is a powder, is not as fine as the iron. I'll just tell you, this was supposed to react more vigorously than the iron did, and I'm a little bit disappointed to see that it didn't. It's certainly producing bubbles. There we go, now it's getting started. Maybe it, maybe there was something that was preventing it from reacting, but now it's making bubbles at a good rate. So that is the chromium. It's reacting a bit more vigorously than the iron even, and now it really legitimately is. Oops, wrong way. And then finally we have zinc. So here are the zinc granules. Put them in the acid, and it's really boiling. So that is the zinc. It's already just about gone. That reaction was so rapid. It's
starting to wind down, and there is no zinc left except for little tiny particles, little leftovers. Before too long, there won't be anything left. Okay, and I actually do want to go back to the chromium. This is more like what I was expecting for the chromium. Pretty vigorous, and we're getting some colors. That's where chromium gets its name. You know, chrome is a Greek or Latin or some sort of ancient language for color. Okay, now we're on the last part. Oops. So now we're on the last part, which is reacting transition metals with each other. We're going to start with a solution of copper sulfate, and the copper ions in solution make this lovely blue color. And we're going to add some zinc powder to that. Our copper sulfate plus zinc powder. And this will take a minute. You can see the zinc on the bottom there. It's already beginning to turn more dark colored. It's black colored instead of the gray that the zinc originally was. I'm going to agitate it a little bit. You know, as I agitate it, it's clearly not a powder anymore. It's aggregating and glomming together. If we wait long enough, and I think it is already starting to happen, the blue color of the copper sulfate solution is going to become less markedly blue. And if we wait long enough, then the black that is covering what used to be zinc powder, it may begin to appear copper in color. It's black right now because it's very roughly textured even on a microscopic level, but as more and more of the reaction proceeds, you might be able to see the color start to show through. So we'll come back and look at this one maybe in a minute. I'll set it aside for now. For these next ones, you're supposed to make a prediction about what will happen before we actually run the reaction. So we're going to do zinc metal again, but this time with an iron sulfate solution. So here's the zinc metal in iron sulfate. And the iron sulfate had that yellow color, kind of like how the copper had the blue color. We're actually producing bubbles here, which I think might just be the zinc reacting with water. Okay, and we'll come and look at this again in a moment. Next we have iron metal. This is the one for iron. Iron metal in copper sulfate. So we're going to get this other copper sulfate solution. We'll put the iron metal in there. And mix it up a bit. It doesn't seem to want to go down. The iron filings are so fine. However, you can see that, oh gosh, I don't know how good the color is for you, But this powder that is kind of getting stuck on the walls of the test tube is very distinctly copper colored. I wonder if a dark background is better. Maybe we'll use Slothy Doffy. Is that better? Or my black book. Does that make for a better background to look at color? Anyway, so that's making some copper colors. And you know what? I put away my elemental copper, so I'll be back in just a sec. Last here we have a zinc sulfate solution with copper metal. And nothing appears to be happening right now. So let's go back and look at some of our others. These were the zinc granules and copper sulfate. And oh shoot, there we are. And I don't know how well you can see it, but there really is some good copper color to that solid down at the bottom. This is the zinc in iron sulfate, and the yellow color of the solution is a lot less. The iron in copper sulfate, and we're seeing some copper color both at the top and at the bottom, at the base. And the copper and zinc sulfate still seems to be not doing anything. Okay, hopefully you can compare those reaction outcomes to your predictions and do the rest of the lab. Good luck.